The focus of today's lesson is going to be kind of taking our transformations for exact graphs and exact equations, and then reviewing a little bit how zeros work with sketches of things. So we're going to do two examples here that kind of just have us writing equations, and then we're going to look into being really specific with our graphs. So I actually want to do example 16 first. Sorry, I know that's a little bit confusing, but because I think it piggybacks most on what we've been doing, the idea that we have to write an equation and they tell us what type of function based on degree. So quartic means degree of 4. So when you multiplied it all out, the highest degree would be 4, but it only has two real zeros. Now remember, our zeros can give us factors. So I expect a factor of x plus 4 and a factor of x plus 6. If I put those two things together in an equation, first I want you to notice I don't have to worry about looking for an a value or that vertical stretch, compression, or reflection, because I basically have no other information. So nothing from the graph, no point it passes through, anything like that. But what it's not meaning here is it's not a quartic function. So there's a couple different ways we could make this happen. They didn't say the multiplicity of the zeros, so I could just make each of these have a multiplicity of 2, and that would be a quartic function. I could make one of these zeros have a multiplicity of 3, and that would be a quartic function. I could actually just keep those two real zeros, and I could write a new factor that I know has no real zeros, something that I know if you set equal to 0 would give you complex numbers and not real numbers, like x squared plus 1. And then I could get a quartic that way. So these are all different ways that you could write that function. Now we're going to get into things that are a little more specific and exact. Notice that example 15 asks for a cubic function, but it is talking about applying transformations. So with a cubic, I would go back to thinking about these types of transformations and how each number affects the graph very specifically. It would just be a cubic rather than a quadratic, which we studied previously. So it says a vertical stretch by a factor of 3. The vertical stretch is going to tell me that the a value is 3. A reflection in the x-axis would also mean that a is negative. Flipping over the x-axis is a vertical type of transformation, because though the x-axis is horizontal, if you flip over it, you're going from up to down. That's a vertical type of change. And then a vertical translation 5 units up, k is what translates or shifts us vertically. That's telling me that k is equal to 5. So this cubic would have an a value of -3. Nothing is affecting b or h. There were no horizontal transformations in this function. So I would just have an x squared here, and then plus 5. So now that you've been reminded of those transformations and how they would write this equation, we're going to look at graphing cubics in a very exact way. So everything we've done in this unit so far has been very surface, like sketching, basics of shapes and behaviors. But this last section is going to get back into the very exact ideas of certain functions, but we're only going to look at the cubic this way. So we're not going to study the exact points in every polynomial, but if we have a cubic and if it can be written in this vertex type of form where we can see the values of the numbers that are affecting it and transforming it, we will change it in that way and have exact points. So the parent function here, so remember the parent function, we want to plug in everything we can. We want to see positives, negatives, and zeros. So I picked the easiest numbers I could on each side of 0, and we're cubing those. And so our parent function is point at 0, 0, -1, -1, 1, 1, and then 2, 8, and -2, -8. And you see that point of inflection we've been talking a lot about in class, like it's going to turn around and then it doesn't. Any cubic that can be written in this form is a cubic that looks like this shape, where it has that one point of inflection rather than having very distinct turning points. And that's because it can be written as this perfect cube. So for characteristics of this, our vertex is 0, 0. That also happens to be our x and y intercept for this parent function. The domain is all reals. You can plug in any type of number and cube it, and you can actually get out any type of number as a result, so our range is also all real numbers. For our increasing and decreasing intervals, this graph never actually turns around. So without a distinct turning point that kind of looks like a vertex, the graph only has one type of behavior. If I follow this graph from left to right, I see that the whole time I'm behaving like an increasing type of object. That means this entire function is increasing, and that would refer to its domain. Remember, increasing and decreasing intervals are domain values, so for all x's it's increasing, and that means there is no decreasing interval. For 1 to 1, remember that we're looking for a yes or a no. This is a function, and it also passes that horizontal line test, so this actually is 1 to 1. Unlike your quadratic, which was not 1 to 1. For the rate of change, this doesn't have a consistent slope, so we're just going to write varies. There's no axis of symmetry here because it doesn't work like a parabola. There's no minimum value because it goes infinitely downward. No maximum value, and the asymptotes are not applicable for this type of graph. So now we're going to look at this with transformations. So first, we're not going to include any horizontal stretching and compressing, and then we are, because remember, our course does do that. So remember, for each of our graphs, we want to start with a parent function. So when you see this is a cubic, you want to make sure you're using a parent function that represents cubing the values that you're plugging in. Then you want to get the transformed function, the new table of values. And so that's going to depend on how the numbers here affect the graph. So then remember, vertically, we have the A value and the K value are going to affect how we adjust our points vertically. And they also tell us that we had a vertical reflection, or if you'd rather say reflection over the x-axis, you can, and a shift down 4. And we can transform all of the y-coordinates with that arithmetic that does a reflection and a shift down. So if I plugged -8 into here, the opposite of -8 would be +8, -4 would be 4. The opposite of -1 would be +1, -4 is -3. 0 minus 4 is -4. -1 minus 4 is -5. -8 minus 4 is -12. The next thing I want to look at are the horizontal changes. We only have one horizontal change here. Remember, that's technically an h value of -6 because our formula is composed of an x minus h quantity. And that would be equivalent to a shift left 6. And we would calculate that by taking the x-coordinates and subtracting 6 to move them left 6 on the graph. Now I will take every x value and transform them in this way. So -2 minus 6 is -8. -1 minus 6 is -7. 0 minus 6, 1 minus 6, and 2 minus 6. Now when I plot these points, even though they're different than the original parent function, I should see something that I recognize as the same shape as that cubic function, even though it might just be oriented slightly different depending on shifting and stretching, compressing, and reflecting. So these are the points I get, and that makes sense with a cubic shape. If I look at it like this, I get that cubic that I was looking for. Now the characteristics of this graph will show us that our vertex, so it was 0, 0, it should now be transformed to those h and k values. So it's -6, -4. And we'll be careful with this word vertex. It's not really like a vertex anymore. It's technically that point of inflection like we've been referring to it, but we're not going to be so strict with that vocabulary. The domain, I'm skipping the x and y intercepts, and I'll come back to them, is -infinity to infinity, and so is the range. So even though this gets reflected or shifted, because it doesn't have a turning point or a distinct minimum or maximum, then we are able to always have that same domain and range. And it will always be 1 to 1. The rate of change varies. There's no axis of symmetry, no minimum value, no maximum value, and the asymptotes are not applicable for this. So with these less turns comes kind of a lot less interpretation of the function. For the increasing and decreasing intervals, as we look at this one, as we go from left to right, we would be going downward the entire time. That means the entire function is decreasing. And remember, you write this as domain values. So the entire domain is decreasing and there is no increasing interval. For the x and y intercepts, we're going to have to solve for those, and it's going to be a little more complicated than it has been in the past. For the x intercepts, we want to plug 0 in for y. And we want to solve. So solving is going to be getting the cubed portion alone, just like we did with the quadratic. So we'll add 4 and then divide by -1. So this will say -4 equals x plus 6 cubed. Now, rather than taking a square root like we did with quadratics, we're going to take a cube root. And with a cube root, you should not be using plus or minus because cube roots include the sign. A cube root of a negative number will be a negative answer. Now, 4 is not a perfect cube, so we're just going to let it stay inside the cube root. And on the other side, we get x plus 6. And to get x alone, we will subtract 6, and we will have this expression that says x is -6 minus the cube root of 4. So that is our x-intercept. For our y-intercept, we're going to plug 0 in for x, and we're going to do this calculation. So this gives us a negative and then a 6 cubed minus 4. That's -216 minus 4, which is -220. That might seem a little bit crazy, but when you look at our graph, look how steep this is, and that y-axis is way over here. It might actually take 220 units. That makes sense before we hit that y-axis. So we're going to look at one more function. And remember, because this function, you see this b value, we really have to rewrite this differently and separate the b value from the x minus h quantity to see the true value of h. And so this gives us an a value of 1/3, which is a vertical compression, a b value of -2, which remember we'll actually use like a -1/2, so that will be a horizontal reflection and a horizontal compression. We have an h value of 2 and a k value of -1. So our shifting will be to the right 2, and since k is actually -1, sorry about that, we will go down 1. So our transformation tables for this graph, we would take those basics of that function and their cube, and then our transformation table for our b will have a -1/2 that multiplies x. For our h, we'll be adding 2. For our a, we'll be multiplying y values by 1/3, and for our k, we'll be subtracting 1. So now we can take each of the x values and y values and transform them appropriately. So for x, I'm going to be multiplying each value by -1/2, then adding 2. So I would do that first with -2. That would give me 1 plus 2 is 3. Then with negative 1 would give me positive 1/2 plus 2, which would be 2.5. With 0, that would give me 0 plus 2. With 1, that would give me negative 1/2 plus 2, which would be 1.5. And with 2 would give me negative 1 plus 2, which would be 1. For 1/3 y minus 1, I'm plugging in negative 8. This is a little harder for me. So negative 8 times 1/3 will give me negative 8/3, and I'm subtracting 1. And I think of 1 like 3/3. That's negative 11/3. Or as a mixed number, because you might find that easier to plot, that's negative 3 2/3. Then when I plug in negative 1, I'd have negative 1/3 minus 1. Because they're both the same sign, it's a little easier for me to figure that that's a negative 1 1/3, but you could go through the same process I just went through previously to do your fraction arithmetic. With 0, I would get negative 1. With 1, I get a positive 1/3 minus 1, and with different signs, it's always a little harder for me. So I'm going to think about it like this, and that's going to give me negative 2/3. And then with positive 8, I have 8/3 minus 1, and that's going to give me 5/3, or 1 2/3. So I can plot those points, 3, negative 3 2/3, 2.5, negative 1 1/3, 2, negative 1, 1.5, negative 2/3, and 1, 1 2/3. So I can still see that cubic shape in there. My vertex, or my h and k value, is now the point 2, negative 1. I'm going to come back to do my intercepts. My domain and range, again, all real numbers. I'll do the things I know best first. So yes, it's 1 to 1. The rate of change varies. No axis of symmetry. No minimum value. No maximum value, and the asymptotes are not applicable for this function. So this function, if I trace it from left to right, I can see is completely decreasing. So my decreasing interval is going to be the entire domain, which is negative infinity to infinity, and there's no increasing interval. And then I'm going to move on to my intercepts. For the x-intercept, we're going to have to do some solving. So when we look at this, we're going to have 0 for y equals, I'm just going to set it equal to the original format of the equation. And then I'm going to go ahead and again work on isolating that portion that contains x, which is all inside the cubic here. So I would add 1 to each side. Then I would times both sides by 3. Then I would take the cube root. Now again here, we don't know the cube root of 3, and that's okay since 3 is not a perfect cube. We'll just keep it as the cube root of 3. And now our job is to isolate x. So I'm going to subtract 4. And then I'm going to divide by negative 2. And this is a little bit nitpicky. You probably won't see them leave the negative here. So you'd probably either see this written as negative cube root of 3 plus 4 over 2. Or they could write it in the other order. Oops, sorry guys. Or if you do want to divide the 4 by 2, you can, but you have to recognize that 2 is still a denominator for the cube root of 3. So any of those will do for our x-intercept. And then for our y-intercept, we're going to plug 0 in for x, which isn't necessarily simple, but it's usually a little simpler in the fact that y is already alone and we just have to follow order of operations. So this will be 0. 0 plus 4 would be 4 cubed. 4 cubed is 64. I'm going to think of 1 like 3/3, and I'm going to get 61 over 3 here as my y value. If you would prefer to write that as a mixed number to understand what it is, that's 20 1/3. And that makes sense with our graph that it might take 20 units for this to climb up and hit the y-axis.